Okay, so I'll just get okay. So I'll just get started. It's nice to see Dr. Jeff Trinkle as well here. At least I see as a co-host on the talk. And thanks for inviting me, David. It's great to see you again. And let me know if my voice gets choppy. And again, I apologize if there's a cat in the background. So let's see. So here, I am, by the way, not assistant professor. I am a mere research professor. I do have an endowment. So the school has been quite kind to me. Which basically means that I don't have to worry about my salary and I can do research. That's kind of the idea. And so I have a big lab. I set it up in 2018. And broadly, I'm looking at terrestrial and aquatic environments. So you can think of like kind of lunar surface or anywhere on Earth on the surface. That could involve terrestrial setting on Earth or aquatic setting, like ocean would cover 70% of Earth's surface. And even if you're thinking geology, I would argue that 70% of that, at least surface area wise, is underwater. So we want to focus on water quite a bit if we are on Earth as well. So planetary Earth, and this shouldn't be a hard thing to convince to this crowd that we are fairly interested in kind of representation of systems, even if it's like terrestrial processes, aquatic processes. We'll see some examples. And so how do we formalize these things? So I work a lot with scientists, planetary scientists, geologists, who are often planetary scientists, oceanographers, and a lot of my learning personally has been, how do we talk with each other, right? Like, and I think some of it now seems to be that, can we represent nature mathematically? How do we do it? Where will our worlds intersect, right? Engineers and scientists, at least the way we used to think about all this. And I think we still do, sort of. So automation science, as let's say a combination of robotics and AI, it's just kind of a buzzword, let's say. So how does it enable earth science and space sciences or exploration? So through my little lens, I feel that it enables things like precision agriculture. I'll show some examples. It also enables geomorphology. I'll show some examples. David, am I coming through fine? Okay.
Sorry?
So,
yeah, everything is good.
Yeah, so we'll see some, thank you. We'll see some examples of precision agriculture, geomorphology, ecology. And my talk actually will not be very mathematical. I'll just try to kind of give present the problems that we are handling. And David happens to be in one of the master's students thesis committees soon. So we will get to talk about that. But if you have questions, do let me know and I'll see if I can answer on the kind of quick array of things that we will look at. So we are all roboticists and people working with data science or some level of engineering, but then what are the problems in nature that we want to solve? So let's assume that we have these sensor networks and some drones with some sensors and some underwater robot, and broadly kind of looking at, let's say, the coastal ecosystem. So I feel that if we look at the question of closing the loop, constantly getting some data and improving some models, and then deploying some robots with some plans and policies, why do we need to redo the experiments? Well, there might be a new disease in a farm. So how do we come up with the representations? Well, kind of as a very casual sense, well, in a linear state space form, I try to convey to the scientists that, look, we could think in terms of dynamics of the environments. Of course, that's and this loop is about kind of understanding those dynamics and then coming up with some policies for intervention in a farm. Now, these are kind of whimsical thoughts, right? It's not like we are there yet, but at least that's kind of the thought process. Can we keep continuing this loop? And then the way we kind of split our worldview is that there's data analysis and kind of data collection, and we are trying to optimally do those in some ways involving various kinds of multi-scale data, satellites, aircraft, drones, sensor networks, etc. And then, of course, part of the education for me has been how to talk to scientists and understand their problems and help them innovate. And I think I am just broadly following what we have been trained to do as roboticists, find representations, good abstractions, and then pitch it as an optimization problem. But then how do you do that for various domains? That's the challenge. So a little kind of flashback of the kind of things I've done, and David was around for many of these. David and I, we have been on a paper. It was mainly his work, so you might have seen some videos of drones docking with each other. I may not have those videos, but we can see that later. But I was quite involved with precision agriculture. So some of these examples you're seeing here are us building our own multispectral cameras, building our own disease monitoring drones that use polarized light at some wavelength, and that light hits a citrus tree. If the tree has something called citrus greening disease, which scientists have found might have excess starch. And I later learned that there are many kinds of starch as well. And that excess starch turns out can rotate the polarization planes of light, a plane of light at some wavelength is the most. So we can leverage those kind of tricks and deploy it on drones. And we got some preliminary kind of good insights from that. And you can map sideways. Those are kind of the ideas, but making these systems and then deploying it. How do you do that? So if you kind of look at the progression of how at UPenn, with Dr. Kumar and Dr. CJ Taylor, how the kind of things we were able to do. And some of this involved, actually all of this involved University of Florida and Penn State University. We were also using their farms. So here, this is an example of if you had a multispectral camera, so not just red, green, and blue. In fact, here, if you just had red and near infrared, you can come up with this product called Normalized Difference Vegetative Index or Vegetation Index, where here red shows a healthy tree, blue pixels show a stress tree or the absence of vegetation. Now here it's now no longer just a camera, it's a LiDAR and a thermal camera. All of these can be together. And remember this was, or rather notice that this was back in 2015 or so. It's already quite a while back. But compute, cameras, can be on a drone. How do you go from data to information? That's the classic problem that we are always dealing with. And then how do you help action improve your signal to noise ratio of your data or improve your maps? So can action guide recovery of data? So this again was done at UPenn. Fruit counting, here it's showing it kind of in 2D. The count goes on. So of course, this starts with some sort of detector, neural network or something else that you wish, but then follows a filtering problem and tracking filtering problem. And then kind of, if you want to localize in 3D, semantic data association. So it becomes very nice and clean and interesting in some sense to deal with these unstructured settings where the semantics or the meaning comes from fruits. Someone annotated a few fruits, so you happen to have some neural network model, no big deal. But then what do you do with that? How do you localize these objects? Can you get me a 3D semantic map? What about a 4D semantic map? Can you tell me later on in 2 weeks which fruits have dropped or things like that, right? The questions could be many. Can you answer those? So this was kind of a precision agriculture arena. This was a collaboration at University of Sydney. What else? Drones. So now we are getting more into controls, which is not necessarily my area, but as we are realizing, we need to do more and more in this. So I'm quite excited to be giving a talk to David's labs. Can you get a leaf sample from a citrus tree in this case? Why do we need a leaf sample? Because there might be a new disease. There's only so much you can do with multispectral cameras and spectrometers. You still need to get a high signal to noise ratio data point, let's say. And that could happen if you look under a microscope or on a molecular probe, then you need a sample. So how do you optimally bring sample? So you saw this nice crash, right? So can we make it better? And we have been working on this, and that's the master's thesis that Daniel will be on in my group. So that's all about kind of stuff I did at UPenn. And here I am at ASU, Arizona State University. I have a nice lab. Even through COVID, we were continuing our work. It has a whimsical logo. I love the logo. One of the group members made. The members are changed, but it's a mix of engineers and scientists. I collaborate a lot with scientists. So typically their students would be coming from that angle. My students are from core engineering, and we together try and do things. So some examples will be presented now from my current work. So I'll kind of go through some real problems around geology. So this work is with an earthquake geologist, a seismologist, and we are studying this area called volcanic tableland up in Northern California, like 10 hours from Tempe and Phoenix, where I am. This area is interesting. The reason it's called volcanic tableland is because a lot of volcanic ash flew like 700,000 years ago from some eruption, and cool down, rock formations happened. There's also some level of ground motion because of the fact that it's not too far from San Andreas Fault. So the question the scientists are interested in is, can you map these tectonic faults or interesting geologic sites, which can be tens of kilometers long, often or more, and can you look for certain properties? So let me kind of articulate what do we mean by particle dynamics and precariously balanced rocks, etc. So this is how the site would look. So you can see a lot of variation. There are the mountains with snow, but then these are the things of interest to us. These rock structures, how they have fractured, but looking at collections of these rocks, what are the distributions of their traits? So when I say traits, I mean it could be, if you're looking at it in 2D, top-down, nadir view, what's the longest, what's the major axis length for rock, if you're modeling them as an ellipse chart. So let's look at, we'll look at some plots. Maybe before that, I should show you the main site. So this extends many kilometers. This goes, some places it will be 10 meters tall, some places it goes up to 30 meters tall. All these fracturing, something caused it. So there are some, was it ground motion? Was it rocks just simply tumbling and hitting each other? Or was it volcanic ash that cooled? Each of these, scientists posit, might cause different shapes of the distributions of these traits. So if you have some camera system on a drone or whatever, maybe a legged robot going and mapping all these rocks, then there will be a variety of questions that will pop up. So mainly it's to answer this thing, like you have these three processes. You have volcanic cooling of this ash that cooled 700,000 years ago. That caused some fracturing, hence certain shapes of rocks and how they look, their major axis length, roundedness. There are various properties that are derived from the main thing. So let's look at mainly kind of roundness or eccentricity, long axis orientation, in this case in 2D. And we want to tell apart, is it due to fracturing, due to collisions? Is it due to ground motions? Kind of it's showing this surface might have moved down, this might have moved up, or is it cooling? For us, let's say as roboticists, it then becomes, how do we map, what kind of pipeline do we need to answer that question? So this is kind of typical pipeline that you would think of, like you fly some drone. I think this is a video. I'll let that. So this is a drone with a multispectral camera flying, not a big deal. Like you can build drones these days quite fast, right? But then the autonomy, so you'll probably leverage a PixHawk flight controller, maybe use the PX4 flight stack. At least that's what we do, because then we can test the whole system before we even fly. So all that is fine. So then what does the pipeline look at? So it just, you can do a lot more. Now we are shifting to smarter trajectories. So 1 second, let me make it full screen again. Kind of lost myself here. There we go. So the pipeline is, the easy part is flying the drone, doing structure from motion, getting like a high resolution ortho-rectified image, getting digital elevation model, even doing the annotations of what concept you care about, of semantics, so rocks in this case, doing some deep learning. So we use scarps and some filtering, image processing. Then we can get to the semantic map of thousands of rocks. So these are polygons showing each rock in 2D. Of course, the bigger challenge is 3D. And then the kind of going from data to information to knowledge is happening, going right in this on this pipeline, where the map with meaning is here. So now you've gone from some good images, nice to look at, but quite useless unless you're a geologist and looking and taking notes. So here we have some information that we can work with. And then we get all these distributions, and now the shapes will be of interest to the geologist, and we can produce various visualizations. And this one is showing that as you go from north to south of the scarp, aspects of rocks change. And this requires some explanation. I'm not going to bother you with this slide. I think I have one slide where I have a little bit, but scarps, you probably already know these kinds of networks. There are many. This particular network can both segment out objects and also kind of do the detection that older, like YOLO, if you're using YOLO version 3 and all, they can detect objects, let's say put bounding boxes, or version 2 at least did that. Scarps can also segment, which means that if you want to detect rocks, you want to know the area of the rocks. Actually, sorry about that, go in front instead of back. So here, for instance, here's an image, here's a trained network. It uses kind of attention features when kind of implementing the network. But the main output is that you can detect all the rocks. So here it's just showing them in distinct colors because it just shows that the network is able to tell apart individual rocks. But then we fly multispectral cameras. We have elevation information. So we don't just use red, green, and blue, or red, green, and blue plus near infrared couple of channels. We also add elevation as something called relative elevation, so that it's always represented through texture, the variations in elevation in that small vicinity. And then we evaluated these things, and we found that yes, adding different wavelengths for rocks, at least adding near infrared helped, elevation helped, and the network behaved better. Those things are covered in our paper in IROS 2020. And for geologists, they are happy because they get to see 12,000 rocks in this case, going north to south, each localized through offline kind of structure from motion mapping in this case. Then they can see how the number of rocks change as they go along the scarp. So the questions that then pop out are there more rocks where the scarp is bending? Scarp meaning this rocky fault scarp, like SCARP. I learned this word only 3 years ago. And then this MD5, it's a measure where they take, for instance, the diameter and then apply this log on that and kind of take it to a metric, a measure that allows them to compare it to an American football. So they can kind of look at this histogram of this MD5 and they can tell how this scarp looks with respect to how the rocks look with respect to an American football overall. But the distribution is what's important for them. And that's where we are on this piece. If there are any questions, please let me know. I'll kind of keep going. So it's 9:20 now, so that I can cover a little bit of geology, ecology, and aquatics. So now I'm kind of beginning to connect on this slide the aspects of geology with ecology. So what you're seeing here is that because we flew a multispectral camera, we also get a good sense of vegetation and other factors. So here it's showing as you go from this bottom part to the top part, you see the lower plane. Here it's showing NDVI. So it used red and near infrared to produce a different kind of index, and the color map here is going from kind of dark gray to green, where green is good, and if you're not seeing green, it's bad, like no vegetation. So you're beginning to kind of see all the bushes and other things pop out, the ones that are alive or healthy or different kind of in between states, you could say. You could also see rocks might have a little bit of things going on, vegetation, etc. And then you see kind of this upper plateau. Some questions that can then pop up are how do they relate to each other, right? So we haven't gone that far yet, but at least the fact that we can see both are interesting. What I would do in the geology space now is move a little bit from the the passive kind of mapping and then doing analysis to what are some kinds of things we can do actively. That kind of brings us to the question of when do we even need to do something actively with a drone? Meaning, like, the kind of things where a drone has to search for something and go close to the object and then map. And well, one area where you'll need that will be where you are not looking at dense rock fields like this, where you have thousands of rocks, but you're looking at fewer precariously balanced features, such as here. If you land up somewhere and you see a rock that is standing, then it means that you could rule out certain ground motions. Hopefully that seems logical, right? Like you show up somewhere and you see a balanced tall rock that also kind of looks old. So you can maybe some high ground motions did not happen. So perhaps you could build a nuclear power plant here as well. So that's the reason why Pacific Gas and Electric has been funding us. Like they have some hydrothermal dams and nuclear power plants. There are some rocks that are around. They just want to generally understand as much as they can the aspects of ground stability in those regions. So how do we map this precariously balanced rocks, fragile geologic features, so that we can evaluate and assess ground motion? So how does this relate with the previous problem that I was talking about? It relates in the sense that I thought I had an image. So let me just draw it out. There we go. In the sense that it again is a story of distribution. So if you see maybe, let's say, 100 such rocks distributed around a certain chunk of California, let's say, and if you could go and map these precisely, so let's say LiDAR plus visual inertial odometry packaged together, and you're getting the data online, doing some corrections offline, that doesn't matter. If you could estimate the centroid of the rock precisely, and then get some information on the basal contact precisely, then you could, with low error, estimate how unstable the rock is through kind of this minimum alpha angle, as like, let's just imagine like, us standing and trying to determine how stable you are. But each rock along a whole spectrum will give some contribution to this distribution, and you can kind of look at a whole site. So the geologists feel that if we can do this, we can characterize large regions. This will be just an additional signal on top of the kind of data they'll get from sensor networks, seismic sensor networks, etc. Except here, it's giving you kind of a fingerprint, or it's like a time capsule almost, right? Maybe I shouldn't say. It's like negative indicator of earthquake, as in if you could study these well, you could say that, okay, in the last however many years, thousands of years, these sort of excitations did not happen. I'll make that a little more specific. So hopefully this part so far is clear. And then we are writing these, doing some new work with Pacific Gas and Electric, where we are trying different things. This is one of our pipelines. In fact, we have moved on from this, where we do the search and map with the drone in the field, and then we kind of do the analysis offline on big machines. So the search and map is happening actively because you can find out where these tall rocks are, but eventually you have to kind of go there. You could very carefully plan a lot more if you have differential GPS maybe, or something like that. But we want to be, we want to develop a general purpose tool chain for tall rocks or tall anything else. So the main things are you have to detect and track the object. So maybe a drone is flying and you see some rock, and you have to kind of do data association and keep track of that. And then you have to kind of localize it enough so that you can plan some path around it. So I can kind of maybe draw it out here. So let's say that's your rock, and that's one rock. So your drone kind of flies, sees that, but eventually you have to kind of maybe do a spiral around it, or an orbit around it. So this flow chart, this schematic is just showing how we have been thinking about the problem of mapping a bunch of these tall rocks. And once these rocks are mapped, then comes the analysis part. So now we are leveraging physics engine. So this is actually Gazebo. Often we run this on the cloud because through some a lot of support from National Science Foundation, we have been able to make all these cloud-based simulation test beds that I use for teaching, for research, and we run some competitions around that. But then the same test beds can now be used. Now, I should mention that this is Gazebo, but not Open Dynamics engine. This is Gazebo using Bullet engine. There are some reasons why we use Bullet when we are doing this geology kind of experiments in this rigid body dynamics environment. But the main point is that if you map a site, I carved out the rock from somewhere here and placed it here. Now it's about doing what this geologists call simple impulsive motion, and 1 meter sudden displacement. And then you could say that, well, depending on who you're talking to. So in fact, if I'm talking to Subrajit, I will be interested in homotopy classes of rock transport. And I think that will be super fascinating. I mentioned that a few times. So from a hazards point of view, you could ask, where will a rock land up? That's interesting. But in fact, we are interested in this to know, so there's fate of particles, and there's also the provenance of, like, where did they come from? That's a much harder problem. So you see a bunch of rocks on the ground. So you could ask the kind of the inverse transport problem. Where did they come from? Now, this rock on the right is the Pacific Gas and Electric near the nuclear power station, somewhere near Diablo Canyon near San Luis Obispo. So a rock has been mapped. So that's the first phase. You fly your drone, get the rock. Then we kind of isolate a rock and then do all these experiments. In this case, it's on a virtual shake table. So we kind of, one of my PhD students developed a pedestal and kind of a tracking controller. And this pedestal is kind of big because it's emulating a large chunk of ground. And then made sure that we can realistically do some experiments for ground motion analysis. Now, we can control the shakes and all that. And then comes, what do we learn from these? So remember that this is kind of not involving the drones per se, right? That all that happened already in the previously. Now we are just looking at, 1 second, I'm trying to, there we go. So now you can imagine that here's the pedestal and here's kind of a matrix, part 1 or part 2, one of the matrices. There's a scene where there's the architect or something looking at all the realities play out. So here is the realities of one rock oriented in different angles. And earthquake motions are being triggered. And this is following established procedures, or I should say, over the last decade or so, many scientists who are working with civil engineers to kind of look at this earthquake stability kind of problem. And these curves, what's not visible here, I can read it out. Let's see. The x-axis is peak ground velocity, the y-axis is peak ground acceleration, I believe, and I'll correct that, but these are the two things that are being measured, peak ground acceleration and peak ground velocity. The main take-home message here is that if I fast forward a little bit, let's fast forward more. You can see that there's a red section and the blue section. So the red is where the rock toppled, the blue is where it did not topple. And some interesting trends start to pop out. You want to see less red. That means that it's quite stable. Like it's and then it's again, you can think in terms of Monte Carlo shakes as well, or you could just look at kind of distributions of earthquake motions. Those things we work with our scientists. But then the take-home message here is that when a geologist, Dr. Arrowsmith in my case, looking at these, they are trying to think in terms of how much red, how much blue, and peculiarities like this. So we are learning that it depends on the rock's shape and the orientation in which the motions came. That kind of effect, like why is there a little island? You know, remember that we didn't repeat the exact same thing hundreds of times. So this thing here. So what if we did this particular simulation again, which itself had many episodes? So various questions popping up, but we are quite excited about kind of this direction, being able to search and map and then get into this mode of analysis. And I'm sorry, I was just adding an equation here. The next, and I'll move on from geology fairly soon. So the next thing is, how do our active mapping operations look? So that's fine. We have a pipeline for search and map. So we have started doing experiments at their site. So this is our current mapping drone. So let's see, what does it have? It has a Z2 stereo camera. It has an Intel RealSense visual inertial odometry tracking camera, also stereo. So 2 fisheye lenses, onboard ASIC, fairly robust. Now the Z2 needs an external compute with NVIDIA GPU. So we have a Jetson TX2, which also helps in the rock detection in the field. And then we have another Intel NUC i5 x86 processor for other computation. Fairly standard configuration if you have seen any of the UPenn drones or kind of generally the community involved in. Yeah.
There is a question in the chat by Jeff.
How sensitive are your red blue zones? So Jeff, you could like maybe ask if you want directly.
Yeah, I was just back at your slides with the simulation. Yeah, these slides. In the earlier video that you showed, one of the rocks tumbling off of a, I don't call it off of a butte, let's say. The dynamic parameters in your simulator, you can control, you can adjust them in some ways and get very different physical behaviors. And I'm just wondering if they are coming into play in this, like if the kinds of things you're trying to extract, kinds of information you're trying to extract from these studies would be very sensitive to those parameters.
That's a probing question. That's the reason we moved from Open Dynamics Engine to Bullet. So we learned that on at least for friction, the way Open Dynamics Engine behaves for low velocities was wrong actually, or off. So it's like it'll be Open Dynamics Engine will be so your question was like based on the parameters, how will the realism change? So at least one thing we learned is that friction behaves slightly differently across at least these two engines. So we have to play around a little bit. The way we will rein this in and constrain it is that we have a real shake table at University of Nebraska Lincoln, and we are trying to kind of match it to that, so that we can, and then at ASU we'll have to through summer build one so that the simulator and the real thing can teach us a little bit. But we don't. So that's a concern. We are trying to kind of correct it as we go.
Yeah.
I don't know if that.
So one of the videos that was just playing on the right hand side, that white rock when it on the right hand side, or at least for me, it's on the right hand side. It's the one that has the command line interface showing.
Okay, this one, yeah.
Yeah. So when that white rock falls, it pauses several times where you kind of wonder if the physics is doing something unusual. And I don't know, like, especially down at the bottom, and there it did. And, you know, there's.
Yeah, so that's fine. So if you that I can explain actually. So this thing, whenever it's pausing, it's doing a lot of collision calculation, is getting queued up. So what you'll notice is the real-time factor will get lower here, where I'm hovering the arrow.
Oh, so okay, I didn't realize we were watching that in real time. Yeah.
Yeah, so now, for instance, this part here is just, so yeah, so that's just, it's just throttling. So there are no inaccuracies there. It was more like when we were comparing what we expect at a very lower level, some of the details around parameters for frictions and all that, it just differs across engines.
Well, right, and but you have some freedom over the types of solvers that you use, and all of that stuff is kind of tricky. But anyway, I'm just curious, and sounds like you're going to start doing some experiments to try to get to the bottom of that. So that's great.
Yeah. So in fact, PG&E, so one of the tasks they funded us for 1 more year is to kind of evaluate those aspects so that we are not wondering all the time, like how constrained are these virtual simulations. Yeah.
Thanks.
Thanks for asking the question. It's really important. Yeah. So now in terms of the search and map, that's what the drones are concerned with, right? They're not trying to do rigid body dynamic simulations on the board. They're trying to get the maps for these rocks fairly quickly. So that's why we have all this autonomy on board. And then the details, like we have some manuscripts on archive as well. It got rejected last year from RL, but since then we have done a lot of extra work, including these experiments. So we start with things in the ASU drone studio. So that's our fake precariously balanced rocks made out of some cardboard boxes with some texture around it. So that's the rock on top of like a pedestal. Mainly Xiang, in this case, the PhD student is testing the, I'm sorry. So Xiang in that case was testing the, so I'll just go back a little bit, the tracker, the detection and the tracking. So tracking by detection is a popular phrase used. And this is just an RVIS view. So the drone studio, so we start with simulations, often on the cloud, like whatever, that's just an ecosystem, then drone studio, then we go to the field. By then, we have to make sure things are fairly robust. Here, we are not even flying really expensive instruments, but like if I put a multispectral camera, that's like $9,000. So I need to be careful about, we need to be careful about how we ramp up. So 2 sites were visited. That one was the rock that you saw in the previous video, kind of that one rock that Dr. Trinkle was asking about. And this is a fault scarp way up in Northern California, not Bishop. But the main point here is, let me just pause a little here. So the onboard sensors are seeing depth image, RGB image, good odometry. We also have GPS, like this is not particularly GPS denied. The PixOC runs an onboard extended Kalman filter that fuses the GPS IMU data. Plus we get the data from the Intel RealSense. So you have a lot of options to how you want to use. Now let's see some of the results. So the typical mission planning that we do in simulation will be like that. The drone takes off. Maybe I should make it full screen, just 1 second. This is already a bit old. I think we have improved since then. So in simulation, we will do this like thousands of times where we can do like Monte Carlo style experiments. First, the search phase, where in this image, the drone is trying to look for a rock and it finds one. And this was during COVID, so you can hopefully excuse us a little bit, but still you need to simulate. So I think mission planning should never be done just in MATLAB or just in your favorite tool. There should be some end-to-end thing going on. So that it's searching, now it's localizing. It has already found it. Kind of uses a particle filter kind of localization scheme when it's looking. Actually, I should repeat it again. So it's tracking, now it's localizing. This kind of error ellipsoid is going lower in represented through particles here. Once it's localized enough, now there are some details there, like how do you know what's localized enough? So you have to get into the kind of the geometry of the rock, and these are polyhedrons. At some point, we haven't gone that, or maybe Gaussian process implicit surface models. We are starting with Poisson reconstruction, but right now just think of it as a rock being localized enough so that you can plan a path around it. So I'll just go kind of fast forward. It's still localizing, and then it fits like this cylinder around it. That's kind of its safe distance. And now its objective is to figure out a way to spiral around. So that's kind of the mission we are perfecting. And we'll have some more experiments this summer in California. Let me see. So that's kind of the idea here. And so we started in simulation, drone studio experiments. We have transitioned to real world. And then we have these additional questions of what do we do with these things when they come back? What I'll do now is quickly kind of go through some of the other topics. I'll maybe show this photo once. That's the drone. So all this is great. It will eventually combination of the drones in the field, getting us the data optimally or near, or at least knowing how far off we are, and then leveraging, let's say, machines on the cloud or in your lab to then simulate these objects, see how they travel with attention to details for the simulators. And game engines are always improving. But it's important for us to understand those physics engines and discuss in the community. But then the hope is that we can solve fate and provenance of particles. Where will they go? Where did they come from? Where did they come from is a hard problem. We'll probably handle that later. So quick kind of jump through, and if there are any questions, I can take it. Otherwise, I'll maybe kind of just start this, talk a little bit of ecology, a little bit of aquatics, and some outreach, and I'll skip some slides if needed, leave 10 minutes per question if possible. David, is that okay? Like, how do you want to do it? Like 5 minutes?
Yes, that sounds good. That sounds very good.
All right, so the question here, which tree is best for cooling? Should I plant the metal tree? Take a minute to think, or a few seconds. Which tree would provide the best cooling for my desert backyard? This is actually, some of it is ASU. This tree, it has slightly thinner leaves, maybe more leaves. This is look like a little more woody. This looks quite artistic, but it's made of metal. I think not the metal, right, David? What do you think?
Yes, I would say C.
C. So David says C. So why not A, right? So it gets interesting. I would argue that trees are like swarm coolers. At least they're helping us that way. Like they're taking in water, they're evapotranspirating. As they're doing it, the thermodynamics of it is keeping the surface temperature of the tree cooler than nearby objects. Plus, it provides shade through its morphology, right? So it's kind of doing these two tasks. It's providing shade, but then this tree is also providing shade. But then the surface temperature is not as good as a tree. Hopefully that argument makes sense. But then the robotics question or the mapping question here is, can you map the morphology of the tree? How big is the canopy, etc.? And then the harder question is kind of the dynamics of the tree. So it's providing some shade, some evaporative cooling, taking some water for that. There's the cost. So it's a good kind of I'm trying to see, the slide has paused. It's a good kind of a question to think about, which means that you have to think about the experiments as well. Like, how do you ever set up an experiment where you know the water use? Well, you just need to think about it and do it that way. And so how do tree species differ in cooling relative to water use in urban drylands? That's the question bunch of us are asking, driven by the ecologists, because there might be more and more drylands as the world heats up a little bit. That's the thought, that we need to understand drylands more and also understand the tools needed to do that, because we might have more it to do in the future. So the tools are quite a variety of tools are available. You can just move your GoPro around or phone and build digital models fairly quick, just to get, like, let's say, a general sense of the topology. But this site here is a desert botanical garden in Phoenix, where we have 15 species, 4 replicates, so 60 trees potted, so we can measure how much water is going in at least. There are certain things that are hard to measure. For instance, how much is it losing just from the soil? So we cover the soil wherever we can of the pots. But it's a little farm where we can move around various sensors. Like this was a sensor that is from earlier last year. And I was telling David that here I'm sort of taking a spring break, but really I'm welding aluminum. That's the sensor I'm trying to improve. It's like one aluminum rig with a LiDAR. And the reason we are using aluminum is, like, in Phoenix summer, it's a lot, the heat, you have to be concerned about it. So essentially I am trying to put sensors on a giant heat sink made out of aluminum. But that aside, you get all this LiDAR cloud. We have spectrometers as well on this. The question is that how do you make sense of this cloud? That's probably not a new problem for roboticists. So we are applying various techniques to model tree trunks and other properties of trees. But the important thing is, once you have the morphology, and let's say you combine LiDAR and multispectral this camera data, can you kind of give me this 3D sense of vegetation and heat? So here you can see some examples of my backyard where I have a litter patch here where any dead leaves and stuff, or dead tree. There was one tree here that died. So it kind of served as the starting point for the litter patch. But like you can see, the dark areas are cooler. The brighter areas are hotter at the bottom figure, and the top right figure, the green areas are more vegetative, the other areas are, and there's some relationship, but of course you want to kind of look this in an automated ways, but we are kind of in the beginning of I should say towards 4-dimensional, so 3D plus change in time, but in the semantic space. That's what we are heading for. But starting with kind of, let's say, the geometric space a little bit, in a sense that how much did the shape change, etc. So this one I will quickly explain. This top right, this embedded thing is a spectrometer reading. I can maybe point out what we are seeing, otherwise it won't make any sense. This axis is, just think of it as number of photons. It's uncalibrated sense of intensity. Just like in a camera, you see brightness. This part is UV all the way. This part up to 700 is kind of blue, green somewhere here, and red. And then this is near infrared. This is called red edge, this little thing here. So whenever the spectrometer is seeing green, it's seeing a red edge. And this is where there's a lot of green in the plant. That's why there's a bomb. So it's seeing all this information as a 2048 dimensional vector. So it's a very rich problem for us to use. And you can think of it as a single pixel 2000 dimensional camera, 2000 band camera in some sense. It's like nanometer. And then we have all our multispectral camera. This one has 6 bands. LiDAR is giving other kinds of information. That's my little dead litter patch where you can see this. So that it's nice that that line stays. So you can see how it's varying from the initial edge that I drew. And then the previous figure, you saw that same patch as the thermal and the NDVI plot. So we are getting all this data, combining robotics and other tricks. The questions we are getting into now are how to fuse all this, how to connect it with the science, and then of course validating all that. And then training the students to use this kind of gear, because we are having to work with ecologists and geologists and kind of convey a robotic style of doing our work. And we have to learn why they're doing what they're doing, and whether we are answering their science question. So in terms of where we are headed in ecology, precision agriculture, I'm ramping up again, working with Dr. Reza Ihsani, and UC Merced is one of Dr. Vijay Kumar's collaborator. We have worked in the past. So this system we are trying to take to the next level. David is just beginning to get involved. He was kind enough to be on the committee, master's thesis committee. So we are kind of looking at one branch of a tree like before, but trying to kind of model it a little more precisely. A lot of simulations is what we started with. Now we are going into kind of drone studio experiments. And by fall, my next master students on this project will probably be hitting a tree again, and hopefully not crashing as often as we did in the past when we were just learning about it. Not too much to say here, this kind of work that has started. We are just trying to ask questions around like what's the correct way of approaching the problem of 10 leaves have been targeted on a tree. I want to get one of those, let's say, or a branch has been targeted. I want to get one of the leaves. So how do we tackle that problem? And the other part that I mentioned was how to map, let's say, trunks of a tree. That's another master's thesis that will be defended very soon towards the end of March, where my student went from the LiDAR point cloud to a 2D depth image, panoramic from the LiDAR, then a neural network that segments the 2D image into trunks. Then he goes back into the LiDAR data and then uses factor graphs to model the trunks. And this can be done in real time. So this is kind of showing a very high level view of that. So at the end of this, you will know, you can think of it as and I am hoping to talk to David and Subrajit and others quite a bit. Like my thought, it's like a metric semantic slam is already in the language, but like this is like we're interested in topology and the metrics of trees. What are some correct ways of thinking of it? I'm hoping to brainstorm with you all. And then like once you have the model of the tree, back to the physics engines. Shade, how much shade does the tree provide is an easier question to answer. If you know the sun trajectories, you can take a whole site. Let's say I want to do this on all of ASU at one point. Just kind of model shade and get kind of average sense of how buildings are being shaded, etc. And then the built environment folks might have interest in that. Maybe they're already doing it. I am asking as roboticists, what are some innovative ways what are some innovations we can add to the existing toolbox? So that's all about geology and ecology. I know I'm running quite out of time, but fortunately, the next few things are going to be quick. Since we have good command over flight controllers and these end-to-end systems, we can fairly quickly build robots. Like this was built within a day or two, and then within a week we had it going around. Direct drive, no gears, no springs. It can hear the ground and feel the ground. So that's kind of setting it up for neural networks. Like if you can, like the thought is that if you can always predict the future, maybe you can model, you have a good model of the world. But that aside, like, we are seeing the ground, but we often don't make use of the IMU data and the mic data if you're trying to reason about geologic properties. That's my argument. And we are trying to keep our drones that way so that it vibrates with the ground. And now I have to see what to do with the data. But it also has a spectrometer and other cameras, so we can do various kinds of analysis fairly quickly on a drone that can, a rover that can be built fairly fast. So these are getting quite quick in our prototyping. And then sensor networks, we always revisit that question. Can we make probes? Can they be a wireless network? And how can they enable other tools? In our case, it's a system of sensor networks, eyes in the sky and eyes in the water, but not just eyes, as we just discussed, ears, and hopefully soon tongue and nose as well through VOCs and things. So to close this talk, some aquatic stuff is also going on. This is not surprising for maybe David. Like I was doing, my dissertation was all on aquatics. Chunk of the world is aquatic. And recently I was watching a talk by John Leonard from last year on SLAM, kind of the overview of SLAM. And he was making this argument that, he tends to likes the aquatic domain because the setting is so complex. And then hopefully maybe if you solve for underwater, let's say SLAM, then maybe it will generalize better. So now when I was doing my dissertation, I was not doing a lot of vision. During my postdoc years, I did that with David and others. So now kind of going back, this is a robotic boat, flight controller, same story as the rover and the drones, very expensive water quality sensor. Now we are asking, can we move this around the water? So we just made a winch. There are no photos of that in this talk, unfortunately, but fairly quickly we can get the data. Now autonomy and closing the loop on change. Underwater, we have built a nice, we are building pipelines for localizing coral reefs, kind of following the thought process from localizing rocks and fruits with better tools. Our center has an aircraft with literally a satellite inside it. So it has an imaging LiDAR, imaging spectrometer and a LiDAR. So it can map whole forests and even reefs recently well, but for coral reefs, you have to calibrate what water does to the sunlight. And that could be site specific a little bit. So that's why we need, so this is Greg Asner, our sensor director. He's also an ecologist, has Navy diving experience from back in the day when he was like 18 or 19, deep sea diving. We don't have too many Greg Asners and Dr. Robin Martin around to be doing this all the time. So we perhaps need some automated vehicles. Can we leverage current drone technology, make something better than those bulky, big underwater robots I used to work on? So this one was the creation over the last 2 years. This year we are improving. The tether is not needed. It's only for debugging. It's literally a drone moving around. So you can kind of see the multi-rotor kind of sense. It just like, buoyancy has compensated for gravity. So it can just go sideways. And it has kind of the same sensors as the drone, a Z2, Jetson TX2. And I am hoping that we can do a lot of aerial manipulation. In fact, there's some level of aerial underwater manipulation that you will see here when it's moving this little pool. Now here I am teleoperating, but I'm sending set points. I'm sending attitude rate set points through a flight controller, but it's all going fly by wire. There's no direct kind of an wire link. It's all going through the flight control computer. So we have multiple master's theses and PhD theses hopefully will come out of this, but the main goal is how do you follow a diver around? So Greg Asner or the experts, when they're diving around, doing their thing, can the underwater drone keep track of it? In fact, the boat and the underwater drone together, can they keep track of it? And second phase, can they then do the mapping on their own? That's kind of the arena we are in. And we'll be doing some experiments in Bermuda, not me, but my students will be going for the boat and the underwater drone, some combined experiments. I think I'll skip all of this. Is actually quite interesting, but I'll stop talking in a minute maybe, and then we can take some questions. This is a panoramic video of this project. So we can simulate experiments before and then compare with the after. And in this case, it's called ExoCam. Whenever they have lunar missions, they'll throw out these little sensors. So let me make it full screen now. This project will continue till June. It started last year. They want to throw out these sensors called ExoCam. And these are right now just GoPro Max 360. And then they'll just kind of see the rocket somewhere. Hang on, let me find it. Where is it? There we go. And there'll be 3 of these. So now we are kind of tackling questions like, can we remove the cage from the video? In fact, I'm just in the process of hiring a student to specifically look at the problem. So a lot of interesting vision problems. Sorry, pause. A lot of interesting, downstream problems that we'll be dealing with. Like we already know how to make the video better. For that, we use a neural network-based filtering algorithm that can take the last 15 frames, let's say, and the next 15 frames in a video and upsample or sharpen, but without injecting artifacts. So it's actually trying to learn a filter of some sort, or at least inducing less artifact. So that's our kind of a Lunar project, which connects with a competition we run, and students in a group are welcome. We were planning to have an outdoor thing this May, but it will probably spill over to October, but we'll have a drone studio experiment going on. This is something we have been doing for a while. And it has generated a lot of useful things. Now, of course, my mission is to make sure that it doesn't just dissipate into ether. I want to make sure these things continue. And the one way it will continue is as it gets embedded into our research ecosystem and when we are eating our own dog food, I feel. I'll maybe skip and just show this one, that's what this competition is about. Like it has to go up, do an attitude rate control to almost like slingshot and throw sensor probes, let's say, into a volcano. And mostly just kind of look at the aspect of I'm trying to see, I had one more video. There's this one. So this is kind of the phase 2 thing. The robotics course that I'm teaching, students are trying to tackle this problem. They'll demo in April. We were supposed to have an outdoor event in May, most likely it'll be in October just for logistical thing. Your students are welcome to attend, just reach out or participate. And so here, there's a down camera servoing, detecting the rover. Or in this case, it's a PX4 rover. It's just a Polaris Ranger with a flight controller. And then the timing problem is kind of being solved. And this was done by a master student from IIT Kharagpur through summer. And you have to kind of drop the ball into that. So on that note, let me kind of wind down some outreach. I do some weird things like building gimbals and using that to and then doing projection mapping through that. And art centers sometimes invite me. We can talk about all this later on. I have a tricycle that's a mapping vehicle. So how will I map all the trees on ASU campus? Well, I have a very good vehicle for that, which can carry a lot of load. It can go for 30 miles. And I think I'll just stop here. Otherwise, I'll keep talking. So let's take some questions. I hope you enjoyed my talk. Yeah. I'll share again.
Thank you very much, JD. Do you have questions?
I have a question here. Question here. So, in the terrain mapping problem, how do you deal with the non-convexity on the terrain? Since you're using like sensors like LiDAR and the depth camera, they cannot travel around in a cave or something like that. How do you deal with this kind of problem?
Right. So do you think that would be an issue if your camera is moving and you can, at some point have a direct line of sight? So
yeah, I mean, for instance, yeah, that's right. Because when you see something that's hidden behind an obstacle, you don't know what's behind it.
Right. Well, that you can't solve, right? You don't know what you don't know. You can have some hypothesis on that.
Okay.
I would say that, yeah, your camera needs to come into the view. Now, if it's a grasping problem, I think people would make some assumptions about the shape of the object on the other side. Similarly here, if it's a rock, I have asked geologists. I mean, we think that it's a fair assumption to make, like if it's the other side of a rock that I can't get to because of some hazards, the drone can't travel. It'll be interesting to ask, like, how will you know, right? So I would say that you can assume that it's symmetric, right, on the other side. But you can't make that assumption for the site, right? Like you can't just, but maybe it's not knowing anything else that might be a fair assumption, but good question. But I would say, yeah, you don't know what you don't know.
Okay, I see. Thanks.
Another question, when the leap separates, if you want to ask directly, you may, I kind of read out from the branch, the mode change in dynamics seems to be a challenge. Where the drones in the video tell you. So the video that you saw was from 2015. At that time, it was trying to do position control, and we were sending the position set points, and it had some level of knowledge about it. Then we tried velocity control. So it was teleoperated. That's the correct answer. Now we are trying to make it autonomous. Yeah, we are not there yet. If autonomous, will teleoperation perform better at the currents? So once it's autonomous, we realize that it's very hard to control the drone, to make it collect a sample. So I think what the correct approach will be kind of assist, right? So you could still guide the drone back and forth, but it should be more like you point out which leaf you want and let the drone do it. I don't know if I'm understanding the question well, but that's where we want to be by this fall. Any other questions?
Yep. Christian,
Yeah. So since you're doing a lot of field work, how much of an impact are things that you can't control? So for instance, I assume there's wind and there's other things. How do you handle those kind of noise and uncertainty problems?
So here's my, let me give a two-part answer. Like if you go and buy a DJI Phantom now, right? And you fly it on a waypoint mission, you'll be fine, right? It's not like your drone will crash. You'll get some data. That's usually a kind of, we always have a baseline. Now, if you're going close to a rock, and in gazebo now they have wind, we tend to avoid flying when it's very windy. I think, so that gets interesting. If we are solving for the science problems, there are some scenarios maybe we don't have to consider, but underwater, that's actually a bigger problem. So when we are considering the coral reef mapping problem, the currents can knock the underwater drone around. So I would say in that realm, I don't have a good answer to that. Like if you're using a multi-rotor drone, you will have some, like let's say you have 2:1 thrust to weight ratio. There are only certain amount of things you'll compensate for, but then you're consuming more power, you're reducing your endurance. So it'll be a trade-off between how long you want to fly and what the quality of the data you want. Yeah. I don't know, David, if you have any thoughts, like it's like, do you want to do robust control? Like what's the paradigm you pick, right? I would say that you could get by just by doing waypoint missions. We don't do that often. Then the question is, we are close to a rock and you might get a sudden gust of wind. Let's say you're doing altitude rate control through some visual surveying. It will be about how you set up that pipeline. But David will have a lot of experience on this, a lot more than me.
I don't think so, JD. You have been in the field way more than me.
Okay, then we can collaborate, yeah, and then figure it out, yeah. But so far, I mostly worry about not putting our drones when they have many expensive sensors in big jeopardy. Yeah, so we try to be little risk averse. So we try to fly smaller drones.
So,
Yeah, Jeff.
So given that you want to be risk averse, which makes sense, then you probably don't want to land and pick up soil samples or anything like that. Already just touching a tree is a big risk, right?
Yeah, so soil sample we have thought about a lot. In fact, we've submitted a proposal. It depends on the terrain, right? If it's uneven, it's probably better not to land and better to lower a winch that takes a sample, because your downwash will already disturb the sample if you go too close. So
and then what if you wanted to pick up some rocks? I mean, obviously that's going to cause a huge increase in the total weight, and then you're going to lose distance, right? But have the companies interested in this wanted you to bring back rock samples?
yeah, it's coming at, like, rock sample return just keeps coming back all the time. And for instance, this video, like in this test, you will see some interaction, but it's not bringing back sample, but on the top one, you will see us throwing rock. It keeps coming, and the problem that we are solving for the tree is actually, I think, harder than rock in some sense, in a sense that it's kind of behaves like a spring damper. But if it's a rock, the drone, at least we expect it to be solid. But it keeps coming up and up, and we haven't solved it. Yeah. But what the kind of things we are looking at is even things like what happens, can we simulate interaction of a particle so this drone has now picked up a little sensor that was lying on the ground that's 100 grams, and you'll soon kind of see it go and topple it on this actual precariously balanced rock in simulation. Now the next thing to ask, and a student has been he has tried on this particular rock, like what if a drone goes and interact with this rock? Now, of course, a drone may not be able to topple it, but just the question of an arm interacting, what should the null space of your arm be? Good questions.
Yeah, well, very interesting challenges.
Yes. Okay, I think one last question. Okay, so
Can I just ask maybe a very quick question? What do you think are the things that you want to solve, like grand challenges that you can tell us?
Well, for me, the answer is quite simple. It's food, water, and environment. Within that scope, what I think what I would like to solve is the 4D semantic change, maybe metric semantic for science. So I've come to a farm. How much has the fruit map changed? Come to a rocky scarp. After, let's say, 3-4 years, maybe some ground shakes have happened. Where have the changes happened? So I would say, yeah, 4D metric semantic change monitoring related to agriculture, ecology, geology, whatever that, like, there'll be some similarities in the setting.
Thank you.
okay, let's thank again JD.